All right, so this is going to be my recommendations for the things you'll want to review for the exam on Monday. I'm going to start by going through your options for things you can go back and review on Wiley, and then I'm going to go over the notes we've covered since day one in the class and point out the things that you're really going to want to focus on as you study. So the first thing is that the exam is 16 multiple choice problems. Most of those will require you to show work. Only 60% of the credit is given for circling the right answer. The other 40% is showing your work, unless otherwise stated on the problem. Some will say no work required, and for those, all of the points count from circling the right answer. They are on a difficulty level, I'd say on par, not with the harder homework problems, but the easier ones, and also with some of the problems that I'm going to point out here on Wiley. So it is 16 questions, but it's not like the Wiley questions that have multiple parts. If a question does have multiple parts, it's been broken up into multiple questions on the exam. So if it were part A, part B, part C on Wiley, it would be numbers 1, 2, and 3 on the exam. So don't panic at the number 16. It's not a particularly long exam if you are confident with the concepts covered. So the first thing I want to point out on Wiley is that the quiz solutions are all posted now. And that is for quizzes 1 through 3, including for quiz 2, we had that optional retake. And so both the original quiz and the retake are on here. And so you'll see that it not just has the answers circled for each quiz, it also has these explanations that I've written up, both for why the correct answer is correct and where possible, I've explained why all of the other answers are incorrect. And I have done that in a pretty good amount of detail for every question on every quiz. So that will help with the conceptual part of the exam. It does lean more calculation-based, but it is good to know the concepts because that will help you with the calculations. And so this is a good resource for that. The other piece, and where I tend to get the quiz questions from, is the practice pages. So you can go in and do as many problems as you want. They are for practice, they don't count towards your grade, but there's lots of conceptual questions and a few calculation-based questions that you can practice here with to get comfortable with the concepts. So I do recommend looking at that for each chapter. Let's go back over here. Okay, that's for the concepts. For calculations, first and foremost, you can go back to your homeworks. And so if you go back to any of homeworks 1 through 3 now, since it is past the due date, it should be the case that you can go in and open the assignment and go to review assignment and see what you missed, as well as what the correct answer should be. And if it happens to be the case that the problem had a solution provided, you can view that, whether you got it right or not, and whether you used all your attempts or not. If that's not the case, and right, some don't have solutions, it's just going to give you the correct answer. But when they do, you should be able to see it. If not, let me know. But that should show up on all of homeworks 1 through 3. The other piece that's going to help you, and for which the calculations are probably more on par with what's going to be on the exam, if not, these may even be a little bit more difficult than what's on the exam. You've got these reference sections under each module. And so some come in multiple parts, but how the reference works is You go in, it has a quick summary of the main concepts covered in that chapter. And remember that I covered some things out of order compared to the book. For instance, chapter 1 of the book is what actually has all the vector things, but I chose to introduce them as we needed them rather than all at once. So you'll want to check back in your book and see where some of these reference things are if you want to use that to put together your equation sheet, for instance. These summary things are a good sort of summary of content to have on your equation sheet, which the equation sheet can be one sheet of paper, 8.5 by 11, front only, whatever you want to put on it. It can be handwritten or typed, and you can put examples, you can put equations, does not matter to me. I will need you to turn that in with the exam though, just so I can make sure that there's nothing that's like, hey, this person seemed to have gotten the exam early or something. So put it together how you want, and that I think will help you study as you put it together. But we go through, it has some practice examples that it does, but then at the very end of each of these reference sections, they've got lots of practice problems. And so instead of the usual Wiley interface where you enter in a problem into a box and then it checks it, here it's a little bit more old-fashioned. We're not worried about significant figures on this exam, so we'll go into, say, some unit conversion stuff. Right, number 3, a basketball coach insists that his players be so-and-so tall, and it wants you to convert a height in feet and inches into centimeters to see if that player would be tall enough. You go through, you try the problem, and then you can check your work with the worked solution. And they vary in the amount of detail they give for these solutions, but they are enough to help you practice in addition to what's been done on the homework. And you can see that a lot of these questions are probably easier than what was on some of the homeworks, and so are more comparable to what's going to be on the exam. But that tells you that if you had no problem with the homework, then you should really have no problem with the exam. Okay. The last thing I'm going to mention before going into the notes is that for homework 4, you're going to want to look at problems 4, 5 will also help you. I didn't write it here, but problem 5, 8, 15, and 16 of homework 4. Those are going to be the ones that are going to most help you in addition to the examples we did in class to prepare for this exam. It will not hurt you to do other problems, but those are the ones that I want to make sure you've taken a look at before the exam. And then the rest you can worry about after the fact. So if you understand those problems, again, I don't expect you to have a lot of trouble with the forces section of the exam. And one last little bit of advice before moving into the notes. So you will need to bring your own calculator. If you don't have one, please let me know before Monday morning so I can get you one. But you'll want to make sure, regardless on your calculator, that it is in degree mode, not radians, because angles will be given in degrees. And if you have it in radian mode, it's going to give you the wrong answer on stuff. And it's an answer that probably won't even be on one of the multiple choice options. So you don't want to have that happen because you'll probably panic and be like, what did I do wrong? And it was just that. And you won't be able to fix it on the exam. So make sure you're in degree mode on your calculator. Now we can move into the notes to see what's really important. So I already did this during the review on Friday, which is today if you're watching this when I upload it. If not, if you missed the review, I went through these notes the same way that we're about to and tried to emphasize what is important for the exam and what is maybe less important. So first day, we were mainly setting the stage for the things we're going to do later. So this whole first page is not something I'm going to test on. Units, we mainly work in SI units, but when we don't, we'll want to be able to convert from SI units to other units and vice versa. The exam is, as far as I remember, primarily in SI units. I don't expect there to really be any conversions you'll need to do, but it is a skill that's going to come up repeatedly throughout the course, so always good to know. Dimensional analysis is not on this exam. It may appear on a future exam or the final, but it is not on exam 1. Trigonometry, as you're finding, does not stop showing up for the remainder of the course. If you're not comfortable with what is on this page, page 6, and then the inverse trigonometry stuff on page 7, you really want to be comfortable with that for the exam. If you don't know trig or are not comfortable with it at this point, that is not going to be good moving forward. So make sure that all of this is second nature as best you can. That's it for topic 1. Moving into topic 2, I'm not going to test you so much on position. We kind of have an intuitive sense of what that is. It's just a point somewhere in space, and we can specify it relative to something else, and then use a set of coordinate axes that are centered at that something else that we're referring to. We use that as the origin of our coordinate system. What you do want to know is what displacement is and how it differs from the distance traveled. And so that's what I highlighted here, is that a displacement is an overall change in position, whereas distance traveled does not care about direction, it just cares how far you went. Displacement ends up caring only about the difference between the final position and the initial position of an object, though, the change in position. And so it does not really care about the path you took to get from an initial position to a final position. It turns out instead, and there are examples here where you can check your understanding of displacement. And the scalars and vector stuff is more distinctions between distance and displacement. It turns out that instead of being the total distance traveled, displacement, its magnitude, the length of the displacement vector, is the shortest distance between the initial and final positions of the object. And so we said that if an object takes some crazy route or goes back and forth, backtracks over and over, that doesn't matter to the displacement. It only cares where you started and where you ended up, and its vector is the one drawn from where you started to where you ended up. Displacements are additive, though. If you have multiple displacements, you can combine them. We now know they add like vectors, but in the case of 1D, meaning motion restricted to being along a single line in one direction or the other, vector addition ends up working like regular old addition. And up here, the equation we can use for displacement is that final position minus the initial position. Again, in 1D, that's essentially just regular subtraction. In 2D, it is vector subtraction. Okay, you're going to want to know the difference between average speed and average velocity. Average speed is the total distance traveled over the time it took to travel that distance. And so it does care about whatever path it was the object took, because we need to know that to find the distance traveled. Average velocity is the displacement of the object over time, and so it does not care about whatever crazy path it was that the object took. It just cares about where the object started and where it ended up. So you want to know that difference, be very comfortable with the difference between average speed and average velocity. Some examples here to help you work on that. Instantaneous velocity and instantaneous speed, although they sound fancier, are probably more intuitive to us. It's the speed you're going right at any one moment is the instantaneous speed. If we also care about the direction we're going at any given moment, that is the instantaneous velocity, the rate at which we're going in a certain direction. And so that's why the instantaneous speed is the magnitude of the instantaneous velocity. And it is important to know that when I say velocity, unless I call it an average velocity, I'm meaning an instantaneous velocity. When I say speed, unless I specifically wrote average speed, I mean instantaneous speed. That's just the convention we use. Then for acceleration, we know that an acceleration is the change in velocity of an object over time. So it's similar to how velocity is defined. It's just now a difference in velocity instead of a difference in position. And the big takeaway from here, since we don't need to worry so much about instantaneous versus average acceleration, since when acceleration is constant, those two are the same thing. What you want to focus on is what it means for the acceleration of an object and its velocity to be in the same direction versus opposite directions. We gave two examples that showed us that difference. It said that if the velocity and acceleration vectors are in the same direction, whether that's positive or negative, doesn't matter, the object is speeding up. Or in everyday terms, we do call that accelerating. And that means it is increasing in speed over time. If the acceleration and velocity vectors point in opposite directions, meaning one positive, one negative, again, doesn't matter which is which, then the object will be slowing down, or in everyday speech, we say decelerating, even though we in physics call either speeding up or slowing down or changing direction, which we don't go over in this part, an acceleration. Any change in velocity, whether that's a change in the direction the object's moving or the rate at which it's moving, is considered an acceleration. And again, instantaneous ends up being, when acceleration is constant, the same as the average acceleration. So we don't need to worry so much about that distinction in this class. If we are looking at position versus time graphs or velocity versus time graphs, we are going to be, there are going to be some problems like that on the exam. You're going to want to understand how to figure out what an average velocity is from a position time graph or some information from a velocity time graph. And so the big things we learned here are that the average velocity is between two times and two associated positions of an object, is the slope of the line connecting those two positions and times on the position time graph. But if we happen to have a straight line on the position time graph, well, then the slope of that line gives us the average velocity. But since it doesn't matter whether we're taking, I'll draw these in blue to distinguish, I drew them in red during the review. So if we take the average velocity between those two times, that time interval, we're going to get the same thing as if we took it between that first point and, I'm drawing black now, and this point. It's going to be the same slope. It's going to be the same slope if we do it between that first big blue point and this point, and so on, all the way up into the limiting case where they're at the same point. So if the position time graph has a straight line on it, then the instantaneous velocity is equal to the average velocity on that straight line. because it doesn't matter how short of a time interval we look at, we get the same slope. Now, if the velocity is varying over time, we don't have the same slope as we look at different time intervals, then we do have to use that tangent line slope and find the instantaneous velocity that way. But I don't have anything like that on the exam, so we're not going to worry too much about that. That would be more of an issue in the calculus-based Physics 1 course. As far as accelerations go, we can get acceleration information from a velocity time graph like we saw in class. We can also get it though from our position time graph, because we said that velocity is, the average velocity is the slope of the position time graph between two time intervals. And instantaneous velocity is the slope at any point on the position time graph. So acceleration, being the change in velocity over time, can be determined based on how the slope of the position time graph is changing from one time to the next. So for instance, in this picture, we see that at this time, right, that time right there, the slope is whatever that slope is. At a later time, the slope is whatever it is there. This time, the slope is whatever it is there. But we see that because this line was straight, that slope does not change from one time to the next. And that reflects the fact that the velocity was the same over this whole time interval, starting from here to this time. And so if the velocity is the same the whole time, it didn't change. And so there is no acceleration. If we have a straight line on our position time graph, then we are seeing a case where there is no acceleration of the object. And so on this first interval, there's no acceleration. During the second interval, there's no acceleration. And then during this last one, there is no acceleration. Where there is between those, where the slope does change. And in this case, it changes pretty quickly, discontinuously, really. It goes from positive to immediately 0. And then it goes from 0 to immediately negative. We don't need to worry so much about those parts. It's just good to know that if we're looking at a straight line, the acceleration is 0. If it's the position time graph. If it's the velocity time graph, then the acceleration is the slope on that graph. And so, for instance, here, this line tells us that we actually do have a positive, meaning not 0 acceleration, because on the velocity time graph, there is a positive slope. So know the difference between a position time and velocity time graph and what consequences that has. Then kinematic equations are, of course, important. They are a pretty big topic on this exam. So you're going to want to be able to apply them. The important piece is not all this derivation stuff. It's just having this table and knowing which kinematic equation to use in a given problem. And so that's why this whole page is circled, because you want to be able to apply the kinematic equations. And so there are some 1D problems, kinematic problems. There are 2D kinematic problems. So if you look through these examples, there should not be anything any harder than these examples on the exam. So just review your kinematic equations and how to use them. Free fall is a special case of 1D kinematics, where for the acceleration due to gravity, we use, for its magnitude, right, the size of that acceleration is 9.8 meters per second squared. The sign, SIGN, of that acceleration depends on if we are calling up or down the positive direction. When we call down the positive direction, or excuse me, down the negative direction, then it makes it so that the acceleration is negative because it always points downward. And so the whole reason that we gave a negative 9.8 there is because we called downward the negative direction. If we had called downward the positive direction, we would have to call our acceleration positive 9.8 meters per second squared. And so it's good to remember that G is just the magnitude. It has no information about the direction of that acceleration. The direction comes in as soon as we specify our coordinate system and which direction is positive and which is negative. So that's what we were seeing here. Same for 2D, in which case we have to worry about both the horizontal and vertical components of that acceleration, but it's the same deal. We don't have any horizontal component. And so we just have to specify the vertical. If we call downward the negative direction, then our Y component for the acceleration is negative, because that's our rule for scalar components. Here again is that case where it's good to know the relationship between velocity and acceleration. When we toss a coin or have anything in free fall, the acceleration due to gravity always points downward towards the Earth and has a magnitude of 9.8 meters per second squared. The effect that has is that when we toss an object upwards, its velocity vector is upwards, meaning it's opposite the direction that the acceleration vector points. And so that slows down the object up until it reaches some maximum height, in which case, if it's 1D motion, it does temporarily stop. It has a velocity of 0. But then after that, it's going to fall back down, have a velocity downward. And so it's going to be in the same direction as the acceleration as it falls. The acceleration's direction and magnitude never changed. The velocity does. And that's why, since the velocity points in the same direction as the acceleration, that you are going to have the object speed up as it falls. We said if the velocity and acceleration are in the same direction, then the object speeds up. So takeaway, acceleration is always 9.8 meters per second squared acting downwards. Velocity can vary for an object in free fall. Vector addition mostly shows up on the exam as it's applied in the force related problems and finding net forces and things. So we'll talk about it more in that context. So it's good to know these general rules. For instance, the tail to head thing is the big takeaway of adding our vectors, but we'll also now be able to say, for instance, in 2D motion, I could ask you about the average speed or average velocity of an object. And so the average velocity depends on the displacement of the object. And so it cares about just the distance between the initial and final positions of the object. In this example, we found that displacement to be 302 meters. So if it took the car, in this case, an hour to drive that distance, no matter what path it actually took, it could be that green squiggly path, its average velocity just cares about the displacement, which is just that vector, the red one, which has this length, the black line of 302 meters. And the direction of the average velocity is the same as the direction of the displacement. The average speed, which we didn't calculate originally in this example, but is straightforward to find, it cares about the total distance traveled. And so I'll go ahead and mark that in black too. So total distance it traveled, assuming that it did in fact just go directly east and then directly north instead of that crazy squiggly path. It's just this length, the horizontal distance it traveled plus the vertical. And so 275 plus 125, that's 400 meters that it drove in that same hour. And so it turns out, even though we got 302 meters per hour for the average velocity, in this case, the average speed would be 400 meters per hour. But again, that's assuming that the actual path that was traveled was going horizontal and then vertical and not that squiggly green path. If we don't know the actual path that the car went on, we can't find its average speed because it depends on the distance traveled. And so if the distance traveled is along that squiggly path, that's going to be really hard to find if we even knew that to begin with. It can be helpful to know vectors are commutative. That's why sometimes I draw vector components one way versus another, as long as they add up to give the overall vector that we're looking at, then we're good. Vector subtraction doesn't necessarily appear explicitly on the exam, so we're not going to spend too much time on that. It's just good to know that in 2D, the kinematic variables are really similar to what they were in 1D. It's just instead of looking at treating those subtractions and additions as scalar subtraction or regular old subtraction, we look at it as vector subtraction or addition, depending on what we're looking at. And so the average and instantaneous velocities, accelerations, all that are defined the same way as they are in 1D. It is good to know that the instantaneous velocity always points tangent to an object's path, whichever way it is the object's going. But otherwise, the 2D versions of the kinematic variables are more or less the same as the 1D. Components, it's good to know. They'll mostly show up as far as looking at the 2D kinematic equation type problems. So we know that a vector can be broken into components, horizontal and vertical, X and Y, whatever the case requires. We can just break it into two perpendicular components. And we can draw those components in this tail to head fashion or as a parallelogram. Does not make a difference. It's whichever you are more comfortable with. It's just sometimes one is easier to draw than the other. Scalar components, you're gonna wanna be able to find these scalar components from a vector description like we have up here. And so really scalar components are just saying, all right, if a vector is pointing this direction along this axis, I'm going to call it positive for the scalar component. If it points the other direction, I'm going to call it negative. It's still going to have the same magnitude or absolute value as the length of that vector component. So we can interchange between scalar and vector components and so scalar and vector descriptions of problems really quickly, just using trigonometry. And you're going to want to be comfortable being able to do that, resolving a vector into its components and then going back to magnitude and direction, the vector description. And so it looks like I have circled the whole page, these two. This example will help you with finding components of vectors. But I'm not going to have any that are strictly like add these two vectors together and tell me they're resultant. It's again going to show up in the 2D projectile motion stuff. So this part, kinematic equations in 2 dimensions, it's what's really important. This first page was just showing that we could do that, but actually applying it is on these next couple pages. So those are the ones I called important. Same as in 1D, it's just being able to apply the kinematic equations to a problem. And so we've got some examples you can look at for that. So I've circled that one as well. Projectile motion is essentially the 2D version of free fall. It is saying that since gravity, the acceleration due to gravity always points downward with a magnitude of 9.8 meters per second squared. In 2D, if we have an object that's launched horizontally as well as vertically, has some angle relative to the horizontal, it's still the case that the horizontal component of its acceleration is 0. And so its velocity never changes over time. It's always equal to whatever it was when the object was first launched. And so just like in 1D, the acceleration due to gravity is 9.8 meters per second squared downwards. And so if you call downwards the negative direction, it is a negative 9.8 meters per second squared component. So that page is also highlighted. This example and the last part of it on the next page are a very good representative of what might be on the test. If you understand everything going on in this example, then the test should not give you any trouble as far as the 2D projectile motion stuff. This does let us see that unlike in 1D free fall problems, it is not the case that when an object is at its maximum height, it has no velocity. It's that it has no vertical velocity component. In 1D, we don't distinguish between the two because the object only has a vertical velocity. But because of the velocity vector and acceleration vector pointing in opposite directions, as the object rises, its vertical velocity component goes to 0 when it gets to the top. But its horizontal velocity, we said, never changes from what it was originally. It's always the same length. And so when we get to the top here, the vertical velocity component 0, the horizontal is just what it was before. So it turns out that the overall velocity of the object when it's up at this highest point is just that initial horizontal part. But then as the object falls back down, we're going to get more of that vertical component back, now acting downward and increasing because it's in the same direction as the acceleration vector. For this whole problem, the acceleration was this y component, negative 9.8 meters per second squared. Again, negative if we called downward the negative direction. And we did in this problem since upward was positive. Okay, so be familiar with that example. I'm not testing on the range. So don't worry about that equation since we didn't spend a lot of time with it. Do make sure you keep Gabby in mind. I'm sure she'd appreciate that. And then we move into forces. So what we've been covering most recently. So for forces, you're going to want to know how to add forces to get a net force. It's just vector addition. If you understand vector addition, you understand how to find a net force. You're going to also want to know Newton's laws of motion. That's what's circled here is the first law, the second law, and the third law. And they're even conveniently boxed for you on the original notes. If you understand those laws, what their consequences are, that's what the whole rest of all these notes is just going through their consequences, what they imply and what they mean. For Newton's third law, it is important to point out because it is easy to get confused on this one. It is talking about the forces between two objects. The force, if object A exerts a force on object B exerts a force back on object A of equal magnitude, but in the opposite direction of the force that A applied on B. If there are no other forces acting on objects A and B, then we can use Newton's second law to get the relationship between the masses and accelerations of the two objects. And it essentially says that the masses, if one mass is much larger than the other, then the associated acceleration of that larger mass is going to be smaller than the acceleration of the other one, the other object, but also in opposite directions because of that negative. That's not saying that the mass is negative for one versus the other. That's talking about the direction of the acceleration vector. So if you understand that and understand that it can happen for any type of force, including the gravitational force, that's what we're seeing here is an action-reaction pair, then you should be good on that. So you want to know that for the exam. And you're going to want to know, not necessarily applying the GMM over R squared equation to find the weight of an object. You can just use, we know on Earth, that becomes the mass times the acceleration due to gravity, which is that 9.8 meters per second squared. So that's the magnitude of the weight. For the direction, it also always acts straight downwards towards the Earth. So good to know that this is how you find the weight if you're given the mass of the object. For tension, the main thing I want you to be aware of on the test is this sort of transferring property that ropes have, that if we apply a force on one end of a rope, it transfers to the other end, like we see here. And also if the rope happens to be very light, nearly massless, the tension that's applied at one end is equal in magnitude to the tension that ends up being applied on the other end, because it takes no force to accelerate the rope itself. All of that force gets to go to the other end of the rope. Normal force, the main thing to take away here is that normal force does not always equal the magnitude of the object's weight. In this case, this block we've got sitting on a table, the normal force from the table pushes back up on the block while the weight of the table pushes it down. So in order for that block to remain at rest, we now know that's an example of equilibrium, no acceleration of the object. Those two forces have to be equal in magnitude, but that is only because of that particular setup we're seeing. The actual action-reaction pair from Newton's third law is the fact that the block has a normal force that it applies to the table due to the atoms on the bottom of the block being compressed. And we can see that the normal force is not always the same as the weight in magnitude from these examples and from the components of a force being in the same or opposite direction as the normal force. So if you're familiar with or understand these examples conceptually, then you should be comfortable on the test and know that even if a force just has a component that's vertical, that still affects the magnitude of the normal force. Then what we've been doing most recently is actually applying Newton's laws in some calculations. So we can look at the case of no acceleration, which we call equilibrium, whether the object is moving or not. So if it's moving at a constant velocity, that's equilibrium. If it's moving, if it's at rest, that's equilibrium. In both cases, there is no acceleration involved. And so we can apply these rules equally to either case. I was asked what we call these equations. You could refer to them as the equilibrium conditions. They follow from Newton's first law, that if there is no net force acting on an object, it will continue in a state of rest or of constant velocity. And so the converse, if an object is at rest or moving in a state of constant velocity, then the net force on it is zero. And we can break that into the components along whichever axes we want to define. And so we did some examples of that. We identify what object we want to look at. We draw a free body diagram for it, meaning all the forces acting on the object. We break those forces into components along some axes, which we can choose to be as convenient as possible in terms of the forces that are involved. And then from there, it's just applying those equilibrium conditions to the problem. And it's essentially plug and chug as soon as you've gotten past that point right there. You just go through the algebra to find what you want. As long as you're careful with your trigonometry, finding your components, making sure you get the right signs on everything, you are good after that. You just need to be consistent with your signs and then your algebra. It was also asked how I was getting sine versus cosine on a lot of these. So that comes from looking closer at the forces involved. So that's T1. If we're looking at the tension from that support rope, we could break that into components by drawing them, excuse me, not that one. We could draw them this way because those add to give T1. Really, T1 should have a little vector hat right now. But we could also have drawn them horizontal and then vertical. Those still add to give us T1. And so depending on which we choose, we end up with a different angle that's of interest in either case. So draw this again off to the side with those magnitudes T1, T1x, T1y. Now this is scalar components. And so we were given in this problem that that angle is 10 degrees. Well, that's a right triangle. We use trig to find whichever components we want. So for instance, for T1, T1x, we have that the T1x is opposite the angle 10 degrees. So sine of 10 degrees is T1x over the hypotenuse, T1, or rearranging T1x at least up to SIGN sine is T1 SIN sine of 10 degrees. The positive or negative part comes by looking back at our diagram, looking at our components. We see that it points to the left, which we call the negative x direction, or here on this picture. And so we know that it is negative T1 sine of 10 degrees. But like I said, we could have used these other components. And so I'll redraw that. T1x, T1y, because those still add to give our overall tension vector, T1. But in that case, that angle is complementary to the 10-degree angle. So it's 80 degrees. Talking about, in this picture, that angle instead of the other one. And so if we wanted to find T1x from this, we would get that it is adjacent to T1 side, and or excuse me, adjacent to the 80-degree angle. And so we would have cosine 80 degrees is T1x over T1, or T1x is T1 cosine 80. And again, it's negative because it points to the left in or in the negative direction in the coordinate system we've drawn. So you would think, well, I got that it's T1 times sine of 10 degrees here, cosine 80 degrees here. Why is the answer different? It's not. The sine of 10 degrees is equal to the cosine of 80 degrees because those are complementary angles, and that is a property of trig functions, is the sine of one angle is equal to the cosine of its complement. Okay, so this was an example of an equilibrium problem, and in particular, what we call static equilibrium because the object's at rest. This is a good example of what's called dynamic equilibrium, meaning the object's moving, but it's not accelerating. And so this is a really good one for practice as far as breaking things up into components, although you won't on the exam have to deal with that the object itself is at an incline relative to a horizontal. You may have forces that are at an angle, but I think that's conceptually a little bit easier than dealing with the object itself being at an incline. So that's a good one to review. And then non-equilibrium, what we've been doing most recently, and what I just posted another video on Wiley for, looking back at this example, is you do the almost exact same thing as in equilibrium problems. It's just instead of using those equilibrium conditions, setting the sum of the x components of the forces and the sum of the y components of the forces to 0, you set them equal to m times the x component of the acceleration and m times the y component of the acceleration. That's because of Newton's second law. This says that this sum of the forces is the mass times the acceleration. The net force is equal to mass times acceleration. So this was an example. Like I said, I did it in more detail and posted that on Wiley. And then this last example is not going to be, there's not going to be anything like that on the exam. It's a little bit more complicated. It's dealing with the motion of two objects at the same time. I'm going to post it as its own video on Wiley later, but it's not something you need to worry about for the exam. That's just so we can stay on track. And if you want to, you can look at it as another example, but there's not going to be anything like that or of that difficulty on the exam. And so that covers the notes we've gone over and should give you a sense of what you want to look at on the exam. So know the difference between non-equilibrium, meaning an object is accelerating, and how you deal with that, versus equilibrium, where the object's not accelerating, whether that object is at rest or moving at constant velocity. You treat it the same way because you still use the equilibrium conditions. And if all of that is comfortable, and you look at those those homework problems I mentioned, 4, 5, 8, 15, 16 on homework 4, then you should be good to go for the exam. Any questions, feel free to email me over the weekend. I'll try to get back to you as soon as possible. But otherwise, good luck, and I will see you on Monday. All right, I will stop it there.